job yesterday. A lot of you volunteered answers. I like you to do that. It makes the class even better for me. Let's take a look at the sheet we did yesterday, and then I'm going to teach you a little bit of new stuff today. The first thing was a mole, and a mole's a very, very big concept in chemistry, and I'll be teaching a little bit more about why that's so important. But people should not tell me I don't understand the mole. You shouldn't say that, because if I ask you about the word dozen, and I've used that analogy many times. So if somebody said, I don't understand dozen, would you say, well, a dozen is just 12 of anything? You get that? So how would you define a mole? Is it really something I can't understand? Can you understand that a dozen is 12 anything? Then what is a mole? It's just not 12. What is it? 6.02 times 10 to the 23rd of anything. Particles, right? So it's not a measure of mass. It doesn't tell you mass. Hey, how much does a dozen weigh? And you say, what do you mean? A dozen what? A dozen cars? A dozen donuts? And so you can't say how much does a dozen weigh, because a dozen has nothing to do with weight. A mole is not weight. It's number of particles. And again, that's what I think is important. Okay, now let's go down. The next thing we did, and we spent days, really, at least 2 days, talking about how to do these kind of problems, these mole problems. And so what we did is we learned how to do this little technique. And so one of the techniques is these things called equivalence. Now, equivalence, it just means something that equals something. And we always start out with, if we're talking about elements on the periodic table, 1 mole, pick any element you want and do it. 1 mole of magnesium equals, it's always going to be this number of atoms. You got that? So if I want to do another one, 1 mole of magnesium equals 6.02 times 10 to the 23rd atoms of magnesium. Now I need to look on a periodic table, because what is the mass of that? What's the mass of a mole of it? And that's where you look over here. And I like to use 3 sig figs. So can you help me on that, Daniel? What do you see there? 24 point. Well, the 4th number will tell you whether the 3rd number stays the way it is or not. Okay, 24? Okay. So this periodic table says, 24.3. So if I'm going to use 3 sig figs, I say 24.3, okay? And so that's how we did it for atoms. Now, what's next? What if you are not talking about atoms, elements? What if you're talking about compounds? Well, what if it's a non-metal compound? The only thing that's different is we call the smallest piece of that a molecule. And what if it's a compound that's made of ions? Well, the smallest thing is called a formula unit. Everybody get this? I've done that several times. Now we go back to the homework. And actually we did a lot in class, but we did this in home. So let's take a look at the first one. If I'm going to do a mole problem with this copper 2 hydroxide, if I'm going to do a mole problem with that, here's my advice. I strongly advise you to write out the 3 equivalents first. Now, it's true, I may only use 2 of them, but I'm going to write all 3 of them out. And that's my advice to you. So if you miss these problems, and I notice you don't write them out, I'll say, that's your fault. If you don't write these out and you miss them, that's your fault. I'm asking you to do that. Now, after you do a few of these, will some of you say, I think I got this. I think I got it. I don't need to write it out, and I still get it right. So let's take a look. 1 mole of copper 2 hydroxide equals, it's going to be this many pieces, isn't it? 6.02 times 10 to the 23rd, and formula units, that because it's an ionic compound. Here's your metal ion, plus 2. Here's your non-metal polyatomic ion, minus 1. Ionic. Okay, that's the only reason why I put formula units there. And now, the last part takes a little bit of work. How many grams would it take to be a mole? And so we look on a periodic table, and everybody look at me, with me. How many coppers are in this compound? Zach, I'm going to ask you some questions because you weren't here, but if you can answer them and they can't, shame on them, right? So what do you think? How many coppers are in that compound? In this right here, in this compound here, how many copper coppers do you see in here?
Just
It's just one. Now you go up here and you find out that copper is 63.5. So we've had one copper, and each copper is 63.5 for a gram of them. A mole of them. And then here's the hard part. How many oxygens are in this thing? See this OH? There's OH. I got two of them. I got two OHs, right? So two OHs would be how many O's? Two. Yes? Everybody got that? Now look up here. How much is each oxygen? 16. All right? We're on to 3 sig figs. And so 2 times 16 is 32. And I have 2 hydrogens, right? All right, and each hydrogen, look over there, is 1. It's way over there. Each hydrogen is 1. And so the number of grams that it takes to make a mole is 97.5 grams. What's the special name? On the test, I'll have vocabulary words, and you can see like stoichiometry will be on there, the mathematics of chemical reactions, you get that? Here's one. What's the definition of molar mass? What's the definition of molar mass? What do you think?
How many grams
Say it. You're right. You got it. How many what?
how many grams are in a mole?
Yes, yes. Isn't that a great name? It's a great name. Molar mass. How many grams it takes to make a mole. You get that? Now, would the molar mass for this compound be the same as water? What do you think? No. They'd all be different, wouldn't it? All right. So then, here's where we went back to factor label. We had learned this in the first semester, but we had to review it. And so the first thing you do is you write down the given. Now, don't leave your labels off, okay? So it's 34 grams of this over 1. Okay, I got that. And now, my own opinion, here's what I would do. What label has to go away? And just write the label. Don't worry about a number. Don't worry about a number. Write the label down here. Next, what label, what are you trying to change it into? I'm changing grams into moles. So just write moles of that right there. Now, underneath my finger, how do I know where to find those numbers? Where do I find the numbers underneath my finger? Because this thing's called a conversion factor, and you get the numbers from equivalence, don't you? Well, that's what these were. This equals that. So we go over here and find grams, and I find the number with that is 97.5. Put it there. I see the word moles. I see the number 1 next to moles. I put a 1 there. And then I take my calculator and say this divided by that. And I am going to get you used to using scientific notation again. And so you just put the little button. Remember the mode button? You know, the mode button? And go ahead and open your calculator. And push mode. And you should see a little box flashing that says normal. And just use your arrow key and go over till it says SCI. And then press that. And then every problem you do now, the answer will be in scientific notation. Now, we did this one in class, so it should have come out to be something like this. 3.49 E minus 1. And E means times 10 to the. Everybody got that? All right. Now, did we do the second one in class? Did we do this one in class? Okay. Now, look right here. Do you think you can do the equivalence without my help? Can you do the equivalence for CH4? All right. 1 mole of CH4 is 6.02 times 10 to the 23rd. And what goes after Avogadro's number there? Why molecules? Because this is a nonmetal and a nonmetal, isn't it? This is a covalent compound, right? So it's molecule. And then how many grams? What's the molar mass? Carbon's 12. Each hydrogen's 1. That's 16. Got it? I'm just reviewing, okay? Next, how do we start the problem? I write down the given. I got it. What label has to go away? Molecules of CH4. Got it. You want to place it into moles? Yeah, I got it. Now go find your numbers and put them where they belong. Okay? All right, now, the trick on number 3. It's not a trick. It's a math thing, isn't it? You don't want to miss this. You've already done the hard work, haven't you? But you're going to miss it because if you have a scientific number in the denominator and you don't put parentheses around it, you're trying to tell the calculator something you don't want to tell it. So you have to put parentheses around it if it's in the denominator. If it's in the numerator, I don't put parentheses around the numerator. only denominator. Are you okay so far? All right. So is that as far as we got yesterday? All right, so do you think you're okay on number 4? Did you guys try any of these last night? All right, look at number 5. You think you'll be all right at number 5? Okay, let's go on down here. How about number 6? Yes. Okay, I looked 5. Okay, how about number 6? I'll go back. Did you know, can I ask you this? I give a quiz to the other class, and you'll have a quiz very similar to it. And I asked them what was the molar mass of something. And I had somebody write this. They wrote all 3 of these down. And I couldn't give them credit because they wanted me to guess which one was molar mass. Look right here. 1, 2, 3. Which one is molar mass? You're right. Is that right? So what if I ask for the molar mass of MgO? I don't want to know 6.02, do I? I don't want to know that. I want to know how many grams it takes to make a mole. Are you with me? All right, number 5, right, Layla? 5? Okay, you tell me, was this what messed you up a little bit?
I know it's grams, I just don't know.
All right, so what are we starting with? Moles of calcium nitrate, right? And we have 4.2 of those, right? So I bet you got that far, didn't you? Okay, now, I want factor label to be a friend of yours. Factor label helps you. It helps you think. Do you want to get rid of the word moles? You say, yeah, I got to get rid of that guy. Moles of calcium nitrate. And don't worry about the numbers. We'll take care of the numbers in a minute. And then what do you want to convert it into? And this is the hard part. I think, Dan, you may have asked that question yesterday, didn't you? And, hey, what are you going to convert it to? They want to know how much it what? Weighs. So we need to convert moles into what? Who remembers that? Kyle, you remember? Into what? Grams, okay? Grams of calcium nitrate. Okay, now, here's my opinion again, and it's a pretty strong opinion. If you know how to write the 3 equivalents out, I would do that. And if you write them out, you're less likely to make a mistake. Every year I do this, and the people who think they're big boys and girls, I'm not writing those 3 things out, and then they put things like 6.02 times 10 to the 23rd next to grams. Why would you do that? Or they put 6.02 times next to 10 to the 23rd next to moles. Why would you do that? Because you think you're a big boy or girl, right? I'm trying to give you some advice and say how to not miss the question, and your pride is taking over, and that's making you miss it. All right, Leda, are you able to do the 3 equivalents for that one? Okay, so I don't want to give you all the answers. It's kind of a homework for you. All right, now what we haven't talked about yet is number 7 and 8, and 8 we have actually. Take a look at 8, and it says which one is a better unit for measuring molar mass. So I'm going to teach a small lesson today, and you'll be able to answer those, and then you can just turn that in next time I see you, all right? Now, we're going to be doing some other problems, and that's what this chapter is about. It's a lot of stoichiometry, a lot of problems. All right, so I'm going to stop that. So I'd like you to go ahead and stop with your homework right now and just say, well, I know how to finish it now. And the only one I haven't taught is this right here. So I need to teach a little lesson about this, and I think it's kind of neat. I didn't hear this lesson. No one taught this to me, and I wasn't even a Christian when I heard this stuff anyway. I didn't become a Christian until I was 31 years old, and I was way past all my high school and even college classes, so I never really linked these together, but to me, there's some beauty here. So I'd like to show you a little bit of beauty in God's creation here. So what I'd like you to do, very, very small lesson. All right, I'm going to show you how this works. If I were to visit the real tiny world, I don't think I talked about the tiny world yet, have I, or not? Okay. If I were to look at the tiny world, and I were to look at a carbon atom, okay, so here's one carbon atom. I'll look at him right there. One carbon atom. And then I also looked at one hydrogen atom. One hydrogen atom. Well, what we noticed is that if I could visit that world, and I can't really go visit it. I don't have a little balance. I can't say, here, carbon atom, let me put you on a balance so I can weigh you. And so I can't visit that world, but we figured out some things. And I don't know if you remember a long time ago when we were talking about protons, neutrons, electrons. Remember that? Electrons have almost no mass. This guy only has one proton. And so how much do you weigh? How much do you weigh one hydrogen atom? And he weighs, I weigh like 10 to the minus 26 grams. Oh, man, I don't like writing that number out. Can we call it something else? Yeah, call me one. I weigh 1 AMU. Now, this is where I need you to think. This is right on the border of what you would teach in non-honors versus honors, okay? I think you can do it. I wouldn't teach this to you if I didn't think you could handle it. But I'm going to ask your brain to do some thinking today. And if I were to go down there, I would find that one hydrogen atom had a mass of 1 AMU. And then when I put the carbon atom on the scale, I would notice it weighs 12 times more. So what's interesting is it weighs 12 times heavier. So as a matter of fact, I could do a ratio. What's the ratio of a carbon atom's weight to a hydrogen atom's weight? And you'd say it's 12 times higher, isn't it? Now that's the way that little world works. And what most people don't understand, here's what most people don't understand. When I look at that number right there, see that decimal number? The only reason that's a decimal number is because, did I talk about jelly beans yet? Did we talk about, okay. Jelly beans, hydrogen jelly beans, there actually are some that aren't the same as other. Do you remember a hydrogen atom that had 1 proton and 1 electron? Remember that guy? He was called hydrogen 1. And then there was one that was hydrogen that had, and here's an electron. And remember, this hydrogen guy had 1 proton, 1 neutron, and what was his mass? His mass was 2. And what about the next one? He had 1 proton, 1 neutron, and an electron. And what were these called? What did you call atoms of the same type that have different masses? They're the same element, but they have different masses. What are they called? So, like the jelly beans, if I had red cinnamon jelly beans, and I picked one up, and one of them had a mass of 5 grams, another one might have a mass of 5.1. They're still cinnamon jelly beans, but they might be a little different, and those are called like isotopes. Now, if I look up here, the only reason that number is not a whole number is because if you were to average 1 million, give me 1 million hydrogen jelly beans. What's the average mass of one of them? And notice how close it is to 1. What would that tell you in jelly bean language? What if you had 100 cinnamon jelly beans, and let's say some of them weigh 5, a few of them weighed 5.1, and a few weighed 5.2. What if you had 100 of them, and the average came out to be 5.001? What would that tell you? And this, again, I'm around that border of can you handle this or not? What would it tell you if the average mass of the jelly bean was 5.001? I got some that weigh 5. I got some that weigh 5.1. I got some that weigh 5.2. But your average is 5.001. Raise your hand if you think you know. It's a little bit higher level. Anybody? Yes.
Is there more like ones that weigh just 5?
Exactly right. You're exactly right. There must be a whole lot of them that weigh 5, right? And because what is the average? What's the average of 5, 5.1, and 5.2? If you're in math class, say, what's the average of 5, 5.1, 5.2? It is? How do you know that? You know, because you learned that trick, didn't you? Everybody, they do this on SAT, ACT all the time, and I don't know why what's the average between 2, 4, and 6? If you have three numbers and they're equally spread apart, the average is always the middle number, isn't it? Add them up. Oh, what? 10, 12 divided by 3 is 4. What? That's magic. Try another one. What's the average of 5, 10, and 15? 10. Well, I don't believe you. 25, 30 divided by 3 is 10. What's the average of 1, 2, and 3? 2. I think then if all these hydrogen atoms exist, then the average should be 2, shouldn't it? But why isn't it? And Zach, you did it. That was great. Why isn't the average atom, why isn't the average mass of hydrogen jelly bean, why isn't it 2? We have three kinds of hydrogen jelly beans. The ones that weigh 1, 2, and 3. You know what the average is? And they've looked at millions of them, millions. And you know what the average is? 1.007. What's that tell you? There are a lot of them, right? As a matter of fact, 99.99% of all the hydrogen atoms we've ever discovered were these kind right there. You get that? And out of a million, there might be 10 of them. There might be 8 of them that have this mass. There might be 1 or 2 that have this mass. This is rare. This is kind of rare. But that's why on the periodic table, that decimal number is not a whole number, because there are isotopes. I'll tell you right now, let me see it. You did a great job, by the way. Here's another one. Don't answer this one because I don't think you know. I think you do know. Do you know that they only know of 2 kinds of isotopes of chlorine? And the 2 that they know of are the ones that weigh 35 and 36. But on the periodic table, it says the average mass is 35.5. All right, raise your hand if you can tell me something. We only know of 2 kinds of isotopes of chlorine. The ones that weigh 35 and 35 and 36. What do you think? Say it again. I can't hear you, sorry.
Is it because there's more 35?
Why would you say, why is there more 35s though? Because I have 35 and 36, and the average is 35.5. What is it? Right, and what's that mean? What does that mean? What if we had 2 tests? You got an 80 on one, and you got 100 on the other. What would your average be? At 90. What if you had 5 tests, and 5 of them were 80s, and 5 of them were 100? What's the average? 90. What do you think?
Would it be that because they were equal, like there's an equal amount of 35s and 36s?
See that? It means if you give me some chlorine, about half of them are going to weigh 35, and about half of them are going to weigh 36. That's the only reason I wanted to tell you what that decimal number. We aren't going to spend a lot of number at that. And so if a chemist says, I want to do an experiment with some copper. There, I want to do some experiment with some copper. Okay, well then what number are you going to use for the mass of the copper atom? And you know what? There are some coppers that have a mass of 63, and some have a mass of 64. So why am I going to use this number, 63.5? Because what do you think's in here? See? Do you think that's only the isotope copper, the 63? Or there are also some 64s in there? What do you think? They're both in there. I can't help it. If I go dig out some copper in the ground, it's going to have both isotopes in there. And you know what? It costs a huge amount of money to separate one isotope from another. It's huge. That's why they never do it. And so what are chemists going to do? Hey, we studied copper a long time, and that's the average mass of a copper jelly bean right there. So I just want to tell you why there's a decimal number. Now I'm going to go back to my story, okay? You all right? I just want to tell you why that thing's there. So here's what I think is God's beauty. I want you to think about this. He gave us a mind. I can't even believe we figured this out. How do we figure about anything about atoms? They're incredibly, incredibly small. How in the world did we ever figure this out? I don't know. It took years. It took centuries. I'll take a look here now. Ready? If I could take you, you ever read that book, The Magic School Bus? Did you ever read that? It's about a class, and they have a magic school bus, and she does something. I think they made an animated series. Raise your hand if you've ever heard of this. Oh, okay. So anyway, we don't have a magic school bus, but if we could go down and take it and shrink ourselves down to the size of an atom, we could do this and find out there was something going on in the little world. Now, I want to be careful here because I'm jumping to a pretty high level thing here. Ready? What if I gave you 1 million hydrogen atoms? And I gave you 1 million, I'm going to give you the same number, carbon atoms. All right, now, tell me how much that would weigh. So I need to get involved here, okay? Get involved, get engaged. 1 carbon atom weighs 12 AMUs. How much would 1 million carbon atoms weigh? Julie, you know.
It's 12 million.
Yes, 12 million AMUs. Is that right? Okay. All right, you're on a hot streak, so here we go. How much would 1 million... Oops, I put it in the wrong place. Darn it. I'm on a cold streak. There you go. Now, Julia, how much would 1 million hydrogen atoms weigh? Each atom weighs 1 AMU. How much would 1 million? Each one weighs 1 AMU. I'm going to give you 1 million.
So 12 million.
What is it?
Or 1 million.
1 million. Okay, now is everybody with me? Can I tell you the beauty? Let me show you the beauty. Whether you like math class or not, this is called mathematics, not math class. It's mathematics. Somebody can fall in love with mathematics and maybe not like math class. So let's do mathematics. Ready? What was the ratio of the mass of 1 carbon atom to 1 hydrogen atom? It was 12 times greater, wasn't it? Let's do this one. 12 million AMUs over 1 million AMUs. And what's the ratio come out to be? If you put that in a calculator, what do you get? Now watch now. 1 carbon atom is 12 times heavier than 1 hydrogen atom. 1 million carbon atoms is 12 times heavier than 1 million hydrogen atoms. Now watch what happens here. This is the beauty. Here we go. You ready? Drum roll. What if I give you this many? What if I give you this many hydrogen atoms and I give you this many carbon atoms? How much did that weigh? Now, I know you want to get your calculators out, but I'm going to tell you something. Careful now. This is going to be so huge of number of AMUs. It's huge, huge, right? But here's the beauty. Watch now. I've already taught this to you. What if I give you, what does this number stand for here, the 12? It stands for 2 things. In the little world, one atom of carbon weighs how much? Now look right at me, okay? Because I'll tell you, I'll be able to know if you're learning this. In the little world, how much does 1 carbon atom weigh on the average? How much? 12 AMUs. But now that number means something else now. If you give me a mole of carbon atoms, and that's why it's a weird number, if you give me this many carbon atoms, you know how much it weighs? It's so many AMUs, it equals what? 12 grams. What? So this number stands for 2 things. If you give me 1 carbon atom, it weighs 12 AMUs. But what if I give you so many carbon atoms, you can't even imagine it. What if I give you a mole of them? I'll give you 6.02 times 10 to the 23rd atoms of carbon. Wow, that ends up being 12 grams. Now, watch right here. Here's some magic here. A little bit of magic. Now, tell me this. Tell me the ratio of how much that huge amount of carbon atoms weighs compared to that huge amount of hydrogen atoms. What's the ratio? It's still 12 times heavier. Oh, beauty, beauty. In the little world, 1 carbon atom is 12 times heavier than 1 hydrogen. Isn't that right? And in the big world, which I can do experiments with grams, can't I? A gram's a paperclip. I can see a gram of carbon. And so in the big world, guess what? A mole of carbon is 12 times heavier than a mole of hydrogen. That's beauty. So the mole concept says, if I can figure out what's going on in the big old world of grams here, I can tell you what's going on in the little world that I can't visit. And that's what I think is beautiful. All right, well now, if you go back to your homework question, let's see whether or not that becomes really easy. Do you still want that out there? Do you need that? All right, let's take a look here. Look at your homework question here. Look at number 7. How are the terms molar mass and atomic mass different? By the way, this decimal number here is called the average atomic mass. See that right there? Got that? Okay, ready. I'm going to help you with this, okay? Molar mass. And matter of fact, I believe Layla already told us. Tell us again, what's molar mass? How many grams there are in a mole? Is that right? How many grams there are in a mole? Now watch it here. A little magic again. How many grams does it take to make a mole of carbon? Let's see. 1 mole of carbon is 6.02 times 10 to the 23rd atoms of carbon equals what? Equals what's that last thing we put in there? Equals 12 grams. So what is the molar mass for carbon? 12 grams per mole, yes? Now, what about atomic mass? So this right here is grams for 1 mole. But what's atomic mass? That means I'm down in the little world, right? Let's go to the little world. What's the mass of that atom? What's the atomic mass? What is that? The mass of 1 atom in what units? What units? AMUs. One more time. If I'm in the little world, and I really need you to understand this because most people don't. Most people take chemistry don't get this. If I pick any element up here, any of them, I'm going to take this guy here. Ready? See that 16? It says 15.9 now. That's 16. If I look at that 16, it means 2 things. It means in the little world of 1 atom, how much does 1 atom of oxygen weigh? 1 atom. In the little tiny world, how much? 16 what? AMUs. Now, let's jump into the big world where I give you so many oxygen atoms, that's a mole of them. Now what does that number mean? What does 16 mean now if I give you a mole of oxygen atoms? It means 16 what? Grams. That's beautiful. The experiments, we can do experiments in the gram world, but it'll tell us what's happening in the little world that we can't see. All right, so what's the difference again? The atomic mass is the mass of 1 atom in AMUs, and I can look on the periodic table and find that number, can't I? If I use the same number, it'll tell me, if you give me a mole of that, it'll tell me how many grams it is. All right, so now number 8, let's see if we can do number 8. Which is a better unit for expressing molar mass? AMUs or grams per mole? Which one of these is molar mass? Grams per mole. Does that make sense? All right. Anyway, I think you should be able to finish this. It should be easy homework for you, like that. All right. Now, you've done a great job so far, but we do need to move on. I did spend a lot of time on this because if you don't understand how to do factor label, then most stuff we're going to do is going to be a waste of your time. So I did spend more